Let's discuss acid and bases in terms of Lewis theory. At the end of this video, you should be able to 1. Explain the Lewis definition of acids and bases. 2. State the reason why Lewis acids accept electron pair. 3. State the reason why Lewis bases donate electron pair. 4. Give examples of Lewis acids and bases. 5. And also give basic illustration on how the process takes place. Lewis acid is a substance that accepts an electron pair. The Lewis definition is more broader than the Bronsted-Lowry definition. That is, the Bronsted acids are not Lewis acid because they cannot accept an electron pair directly. Lewis acids include not only proton donors but other species as well. That is, the Bronsted-Lowry acid is limited to compounds containing hydrogen. However, the Lewis definition of acids and bases are more useful. The figure contains images of Lewis acids. It is less obvious now that many transition metal compounds are excellent Lewis acids, as shown on the screen. The bonding in such compounds is complex since it involves d orbital hybridization. But all of these transition metal compounds have a vacant orbital that can accept electron pair. Let's now discuss the concept of Lewis base. Lewis base is a substance that donates electron pair. It is important to note that Lewis definition of basicity in a compound is quite similar to Bronsted-Lowry definition. A Lewis base has a lone pair of electrons that it can donate to a Lewis acid for use in forming a new bond. In a more general sense, we can then say that most oxygen and nitrogen containing compounds are good Lewis bases because they have lone pairs of available electrons. For example, alcohol, ether, aldehyde, ketones, acid chloride, carboxylic acid, esters, amide, amine, sulfide, and organotriphosphate ion are good Lewis bases because they have lone pairs of electrons that they can easily transfer or donate. Now, let's discuss these basic illustrations we have on the screen based on the explanations and the definitions we have discussed so far. For the example 1 there, we have hydrogen ion reacting with hydroxyl ion to give us water. The hydrogen ion there is acting as a Lewis acid, while the hydroxyl ion is acting as a Lewis base. Now, the hydrogen ion there has a vacant s orbital, while the hydroxyl ion there possesses lone pairs of electrons. So we can see from the arrow sign that the hydroxyl ion, which is a base, is donating lone pairs to the hydrogen ion, which possesses a vacant s orbital. So from here we can deduce that the hydrogen ion is a Lewis acid, while the hydroxyl ion is a Lewis base. For example 2, boron trifluoride is reacting with an ether. The boron there has a vacant p orbital, while the ether there has a lone pair of electrons. So as we can see from here, the ether is transferring a lone pair of electrons to boron because of the vacant p orbital. So we can say therefore that boron trifluoride is a Lewis acid, while the ether there is a Lewis base. For illustration 3, we can see that the nitrogen there has a lone pair, that is a nitrogen in trimethylamine, while the aluminum there possesses a vacant p orbital. The aluminum trichloride there is a Lewis acid, while the methylamine is a Lewis base. Now, in conclusion, we can say that a Lewis acid are electron pair acceptor because of their vacant orbital. A Lewis base are electron pair donor because they possess lone pair of electrons. Some transition metal compounds are Lewis acids. And finally, the Lewis definition is a more broader one.